By next week, for this part, I think within 1 hour, I will just finish this. Okay, so next week will be this part. Now, last time I have discussed with you some of the concept of the simple linear regression. Why do we call it simple linear regression? What is the variable involved in terms of the y and x? What are the names? How does the relationship between the two variables? If it is positive, if it is negative, and so on and so forth. Okay, so I think I have discussed this last time. So for if you can look at the same time at your textbook, so I'm starting my discussion with the example 5.1. Okay, so that will be on page 167. Okay, so last time I have shown you why do we need to have the scatter plot before we can even do some analysis on the simple linear regression. Can someone tell me why do we need to do the scatter plot first before we do the analysis? Can someone please? Or if you forgot, you can just say, do remember, so that I don't need to wait for you for your answer. Can someone please? Why do we need to have a scatter plot for our data? Try faster. Class. Class. Keep quiet, everyone. I have discussed about this, right? Simple sample linear correlation coefficient. Now, before we can do the analysis, okay, by somehow if you can calculate or if you use your Excel or whatever software to help you out with the measurement that you are looking for, okay, the reason why we plot the scatter plot is because we need to have some insight of what our data is telling us. Okay, so for example, if you're looking at example 5.1, you have the physics score and mathematics score. So you have like 1, 2, 3, 4, 5, 6, 7 data set. So in this case, what you can do when you have your scatter plot, you can imagine what would be the relationship between the two variables that you have in hand. Okay, last time we have discussed it can be positive linear relationship or negative linear relationship. If it is positive, it will be as x increases, y increases, or it could be negative as x increases, y decreases. Okay, so as x increases, y increases. As x increases, y decreases. So that's how your relationship will be regarding the two, or it could be no relationship at all where your line would be flat line. So this will be no relationship. Now, this is why you have to do your scatter plot, just to give you an idea how does your relationship looks like, and it could be somehow tells you whether your sample correlation coefficient, your R will be strong or weak, just by looking at your what we call scatter plot. Okay. Now, last time, how do we know that a data will have a strong relationship? Class, can someone tell me? Last time when we discussed about strong relationship between x and y, and the r will be approaching +1 or -1. Okay, so if you look at this particular figure, you know that whenever you have a data set of x and y where the plot will have a kind of a straight line, so this is what we call perfect relationship. Strong relationship means that both of them have really strong relationship positively, whereby it becomes a straight line of the given scatter plot. Okay, so that's how we figure out whether our scatter plot or our x and y is strong or weak based on the scatter plot. But the actual value for strength will be given by the correlation coefficient R. Now, I would like to show you how you can do your scatter plot using Excel. Okay, so let's say you have your example 1, physics and mathematics score. How do I come up with this particular scatter plot? Okay, so I have mathematics score, I have physics score, and I know the mathematics score is referring to my x, and physics score is referring to my y. So don't miss up putting this become x and this become y. Okay, so basically simple linear regression will follow x as the horizontal and y at the vertical. Okay, so let us see how we can do the scatter plot using Excel. Now, can you see my Excel class?
Yes.
Class, can you? Okay, now I have my data here. Okay, now bear in mind, class, yeah, this is why I put some notes here. Bear in mind, if possible, when you key in your data set, do not start with Y. Okay, so if I follow exactly as what my textbook give me the data, I have my physics in the first column and mathematics following column. But what happens if I plot using this data? Okay, because I don't want, I know I can change the setting using the setting of the graph, but since I don't want to, I want to minimize the the function of x and y and putting in terms of the scatter plot. So I directly urge you, if you can, please put your x in the first column, followed by your y in the second column, because it will be y. If you put y first, then your scatter plot will read your y as in your x here. So if I show you, this is why I mistakenly take the x and y. Okay, so this is wrong. Why? Because first data should be 65 for x and y what? 65 for x and y 60. So what happens if I plot? I have my x become 60, my y become 65. So it's kind of swap. Okay, so they change the okay, okay, they change the place here. Okay, so they change the place. So please make sure you are referring to the correct axis. So if let's say I use my x in the first column and followed by my y in the second column, so what happens is that, okay, I will start highlighting my data, go to insert, choose scatter. Okay, choose scatter. So what happens if you choose scatter? It will give you this chart. Let's say I do it again. Okay, because I have done it before you. Okay, so you can just start by not clicking the data, but I usually click my data, then go to insert, go to scatter, choose the scatter. But what happened here, class? Okay, your what we call your horizontal and vertical line is not maximally or is not optimized in terms of the initial value. So the given horizontal and vertical begin from 0, and when we look at our data begin with the least will be 60 and 65. So what you can do is that you adjust the what we call the vertical and horizontal setting. So what can you do? Go to Access. So if I'm too fast, let me know. Go to Access, click the bar and then click more option. Okay, so when you have this, so you will have option here, axis option, bounce. Means that bounce is referring to the axis of the line. Okay, so here it mentions 0. Now I want to change it here to, the list is 65, so I want to make it 60, for example. Okay, make it 60. Okay, and then the maximum is, if you can see, your X maximum is like 97. So I'll just put 100. Okay, so finish for my horizontal. Then I change for my vertical. Choose vertical axis. Okay, do the same. Change to, since I have 60, so I would like to have, let's say I put 50. And then the maximum is also 100. Okay, so what you do, you will have this particular scatter plot, which is much better, and you can see clearly from the beginning of your minimum value to your maximum value. Okay, so you can change this. So since I don't want to have any title, so in my case I don't want to have any title, so you need to change to add the axis of X and Y. So go to design, go to add chart, go to primary horizontal, and put your axis. So let's say in this case is just put maths. Okay, then go to add axis for Y. Okay, and put for physics. Okay, whenever you do your whatever things here class, please check whether your data is according to the correct source or not. Okay, so that's how you do your scatter plot. So you can change your scatter plot setting in terms of the font size and everything, font type and everything. You can, if you want to have circle here, you can change it to diamond or whatsoever shape that you wish to have. Okay, so what can you do from this first example? Okay, so you can see as X increases, Y also increases. So you can see here, okay, your first part will be, okay, physics and mathematics will have linear relationship and their relationship is positive. Okay, when I say positive means that as X increases, Y also increases. So do you have any question in class?
No question.
Okay, thank you. If no question, we move to the second part. Okay, so the next question also the same, but now there will be a difference in terms of what is inside the data. Now you are being given this particular data, age and net worth. Okay, really sorry for the typo. A researcher wishes to see if there is a relationship between age and wealth. So X as age, Y as the wealth. Okay, of the wealthiest people in Malaysia. Okay, now let us see how we can construct this using Excel. So I have my data here, my X and my Y. Okay, so I just quickly show you how we can put that into your scatter plot. Okay, okay, so once you have this, so if you can see, if you don't change the setting of the vertical and horizontal line, so your scatter plot will not be so nice. Okay, so change them according to what I have shown just now, and if you can change that accordingly, so what you have is this is your scatter plot for age and net wealth. Okay, when you see this class, okay, in statistics, your eyes should be very sharp in terms of finding the pattern of your data. Now, if I were to analyze this particular scatter plot, okay, if I look at it first glance, okay, I may assume that the line could be this one, okay. Okay, so our first eye could be, okay, this could be the line, but it's too much. If this is the line, this will be considered as outlier, too far away from the line. Or is it this way? Could be possible. Okay, or is it this way? Could be possible. But if you look at your line compared to what you have in 5.1 just now, obviously you can see the line. Okay, so in the second example, this is what happened where your x and y is not really has the what we call linear relationship that we are talking about so far. Okay, so in this case, when you pair them according to the least to the most, okay, and if you plot them, you cannot find such linear pattern from the scatter plot. So in this case, okay, we cannot say as x increases, y also increases, because somehow your data shows that as x increases, um, for example, I would like to have x increases and the y decreases. Okay, for example, 86. Okay, 86 here. Okay, so if you can see here, 86 you have 2 points. So if one of the y is 4.6 and the other y is 2.2, so we cannot really tell does the relationship is positive or negative. But based on the scatter plot, we might say that okay, we cannot really tell whether this h and x, h and that well is having what we call linear relationship. Okay, so that will be based solely on the scatter plot. Okay, any question so far, class? Any question? No, huh? Now, we know that once we have got our scatter plot as our first analysis using our eyes, okay? We use our eyes to see what will be the pattern of our x and y relationship. Now, there will be second device or second way on how you can tell about your relationship of x and y. That is using your linear correlation coefficient, or we call it as R. Okay, we know we use the notation of R. And R is actually obtained by the sum of square between the x and y variation. So this is regarding your x and y. And divided by the variation of each x and y. Okay, so you can see how the correlation of coefficient for your sample is obtained. And I have discussed how you can tell from your R value whether it will be the direction will be negative or positive, and the strength is whether it will be strong or weak relationship. Now let us look at the example 5.3. Okay, so example 5.3, you can look at 169. Okay, refer to example 5.1, calculate and interpret the sample correlation coefficient. So class, if you look at your textbook on page 169, you have this particular table given in your data, in your solution. Okay class, so this is what we call as summation of x, summation of y, summation of x squared, summation of y squared, summation of x and y. Okay, and from this particular summation of x, x squared, y squared, x, y, and everything, you can find your sx, y, sxx, sy, y. So this is the what we call variation that involved in this particular data set. So that's why that's how our R is obtained using this particular measurement of the variation between your data. So because we are not going to discuss on the manual of the sample correlation, so I would like to show you how you can use your Excel to find your sample correlation R. Okay, let's move to example 5.3. So please refer to my Excel. So if you can see from my Excel here, okay, all this summation, okay, can be put into your SXX, SYY, SXY, and everything. And finally, based on the calculation, you can get your calculated correlation sample correlation coefficient. Now, what if I'm using my Excel, and how does my Excel result looks like? This is your result if you are using your Excel. And how do I get this? Okay, so class, look carefully. Okay, so let's say I do it again here. Okay, go to your data. Okay, go to data analysis. Okay, find correlation. In your data analysis, take correlation. Take the input range. Okay, since I have label here, so I would like to take my data label in my calculation. So I put my data label as well and group by column. Yes, I have my first column mathematics, second column physics, and then label in the first row. Okay, and I identified where will be my result. Okay, so I just click for one box and then click OK. So this is your result. Okay, so this is your result for your correlation. Now, what does your result show? Now, the one that we are interested in is between physics and mathematics. So we go for physics row and mathematics column. So this will be your interested figure that you need to interpret afterwards. Why mathematics and mathematics you have complete or exact correlation 100% is because definitely mathematics itself will be having one correlation because you are talking about the same variable. Okay, so that's why physics and physics you will get one. So we are not interested with this particular value, but we are interested this in yellow color value. So we know that our sample correlation is 0.991, which is similar to your calculated R. Okay, class. So far, do you have any question? Class?
No.
Okay, clear? Okay. Thank you very much. If you do not have any questions, okay. Remember, just now we are talking about the scatter plot of our data, and it seems that your R, which is almost 1, okay, reflect clearly from your scatter plot. So because if you draw a straight line, most of your points will be near to your straight line. So this will be an indicator why your R is approaching positive 1. They have direction positive, okay, and the strength is very strong, very high, okay, because approaching 1. So that would be our example based on mathematics and physics core. What about the second example? Okay, so if you look at example 5.4, okay, so that would be on 170. So please look at your data on 170 for example 5.2 just now. Okay, we know that our scatter plot is just look like this. We don't know exactly the direction of our relationship, whether it is positive or is it negative. Okay, so far we can exactly tell. But what if we find the sample correlation coefficient R? Okay, by using Excel. So I find this particular result. And it seems that the sample correlation for age and network is given by 0.0461. So if you look at this particular value, it is very small. Okay, we know that. Okay, we know that. There's no color. Okay, we know that if we have from -1 until +1, we have in the middle is 0. Okay, so that would be the range of our R. Now our R is equal to 0.0461, which is near to 0. So we know that this particular value shows weak relationship between the two variables. Okay, so in this case, up until sample correlation, we know our sample correlation shows that for this particular data, they have weak relationship. But we still do not know whether they are positive or negative. Okay, class? Clear, class, for the second example for the sample correlation R? Okay, eh?
Clear.
Okay, thank you. Now, let's move to the next, what we call, okay, I've shown you inside the slide actually, but since I want to show you the Excel, so it's okay. So finish with the scatter plot. So done with scatter plot. Please remember what is the purpose of scatter plot. Then sample correlation coefficient. Okay, our R. Done. Okay, so please remember what will be the function of this particular scatter plot and correlation coefficient R. Now, there will be if you turn to your page of your textbook on page 171, okay, there will be a part of the hypothesis testing for population correlation coefficient rule. Now, you know that you are dealing with this particular data. Okay, from our scatter plot, we can identify whether our direction will be positive or negative. Based on the correlation coefficient, we know whether our relationship is strong or weak. Okay, but now we want to test, okay, whether there is exactly a correlation between the two. Okay, so we need to test for the hypothesis testing for the significant linear correlation between X and Y. Means that you are testing whether your X and Y really has what we call linear relationship. Okay, so to test for the linear correlation between X and Y, you are going to do hypothesis testing referring to your rho. Why rho? Remember class, we are dealing with statistical inference. We are talking about our population, right? And since we don't really have enough time, money and everything, so we focus on our sample. Okay, remember last time when we want to make inference for our population mean, we use our population sample X bar. The same with this particular case. If we wish to test for the correlation between X and Y, okay, so we are going to test for the rho. Okay, we use rho to represent our what we call sample correlation. Okay, our sample correlation, I don't remember what is the location. Can you see somewhere in your textbook what is the sample correlation? Okay, but the sample correlation I can't remember. Okay, so sample correlation, we are going to make inference using sample correlation to make inference for our population correlation. Okay, So that's why we are going to test. And the way we test, we are going to use this one. Now rho equal to 0, now not equal to 0, and we can clearly see this is what we call two-tailed test. Okay, so we are going to look how we can test this particular population correlation coefficient. Now, let us look to the same exact example of mathematics score and physics score. They performed the hypothesis test for the significance of linear correlation between physics score and mathematics score in example 5.1 at alpha 0.05. Now we have seen just now how we can begin with the scatter plot. Okay, and later we'll see how we can find our sample correlation coefficient for our physics score and mathematics score. Now we wish to test is this 0.991 is acceptable, is correct to describe our relationship between x and y, mathematics and physics. So let us look how we can test for this. Okay, so we begin with the first step. Okay, so our first step is either you choose to have this only as your null and alternative statement, or you can use this particular sentence to show your statement of your hypothesis. Okay, so if rho equal to 0 means there is no linear correlation between physics and maths score. So you have to mention what are the variables involved into your statement. Rho not equal to 0 means there is a linear correlation between physics and maths score. Now, second step, as usual, critical value. Okay, so since we have our n, how many n? 1, 2, 3, 4, 5, 6, 7. Okay, since we are dealing with what we assume to be normal data, since our n is less than 30, okay, so we are going to use our t alpha n minus 2 as our critical value. So that's why we have here, given our alpha 0.05, our n equal to 7. So our critical value would be 0.05 divided by 2, 7 minus 2, you will get 0.0255. Now let us look our t table. 0.05, 0.0255, 0.0255. 5 degree of freedom, 0.025. So you have here 2.5706. This one everyone clear? So this is how we find our T critical value. Okay, class? Are you all okay, class?
Okay.
Okay, thank you. So we go back to our slide. So we know that our data just now give our critical value is given by 2.5706. But since we are dealing with two-tailed test, that's why we put plus minus, because we don't know what will be our value of our test statistic. So in this case, if you can imagine, you are dealing with normal distribution, but this is for student or t distribution. So we have our negative 2.5706 and positive 2.5706, where this is given by 0.025. This one also given by 0.025 alpha over 2. Now, okay, now go back to our third step, find the test statistic, and your test statistic will be using this particular formula. R is your sample correlation coefficient, okay, the one that we obtained just now. Okay, and then n is your number of data, and then r squared is also referring to your r. Okay, so we know that our r just now is 0.991. Yeah. Okay, so take that value and put into your calculation of t-test. Okay, test statistic. Okay, so put everything accordingly and you will get your test statistic is 16.55. Okay, so if you put into your t distribution, you know that 16.55 would be much further away from your Z critical value. So let's say this is your t test. Okay, so sorry, I'm mentioning about Z just now, t distribution. Yeah? So this is 16.55. Falls in the rejection region. So that's why we reject the null hypothesis. So reject the null hypothesis means that we have sufficient evidence to support our or to conclude. Okay, if you would say there is sufficient evidence to conclude that there is a significant linear relationship between visit and net score. So since our R just now is 0.991, it seems that you have strong evidence that, okay, this particular physics and net score has the, what we call, linear relationship between them. Okay, class, clear? Okay, class?
Clear.
Okay, now let us look at the exercise. Okay, I purposely did not do for 5.2 just now. Okay, so let me check, do I have in my Excel? It's 5.4. I didn't do it. Okay, it's okay lah. Okay, so let us look at the exercise that you have on page 173. Okay, now you have given the data for the number of rooms and kilowatt hours in thousands. So when we say in thousand, means that this one is actually 27,000. Okay, 24,000. But since the figure is too big, okay, so in thousand means that everything is, it should be in thousand, so that's why they just put it at 27, 24, and so on and so forth. Okay, so what do we do here? AMN tenaga elektrik Sdn Bhd wants to determine the relationship between kilowatt hours 1000 used in the number of rooms in a budget hotel in Kanga Place. A random sample of 10 hotels yielded the following. Okay, so you have the number of rooms and the number of kilowatt hours. Okay, but in this case you don't know, you are not being notified about what will be your X, what will be your Y. So can someone guess which one is your X, which one is your Y? Class, which one is your X, which one is your Y? This
Number of rooms is X, Y kilowatt hours is Y.
Okay, thank you. Why? Do you have any reason? Okay, good try actually. Yes. If we would say number of rooms depending on kilowatt hours, it would be sounds awkward, right? Of course, the usage of electric, okay, is based on how many number of rooms are being used by the customer, right? So in this case, that's why kilowatt hours is depending on your number of rooms. The more rooms being used, okay, the more kilowatt hour will be. So that will be our assumption for this particular relationship. Okay, so identify the independent and dependent variable. So as you mentioned, as your friend mentioned just now, your dependent variable, okay, would be the kilowatt hour. Okay, and your independent variable would be number of rooms. Okay, Now, second, by using our Microsoft Excel, sketch the scatter plot. Is there appeared to be any linear correlation between the variable? So let us see how we can do this in our Excel. Okay, example 5.5, exercise 5.1. Okay, so we may have our data here. Okay, number of room and kilowatt hours. Okay, so if I draw my scatter plot, okay, do you want me to show, or I'll just straight away use my scatter plot ready here?
Use your scatter plot.
Okay, thank you. Okay, so we have our scatter plot. So everything I have adjusted according to this right scale. Okay, so we have number of room at the x-axis and kilowatt hour in the y-axis. So everything's okay. Now, based on this, what can you tell, class? Is the line like this, or is the line like this? We don't really sure, right? So in this case, what can you tell from this? We don't really have a clear picture of what will be the relationship for this particular two variable, right? But if you look at your this is just because we do have the answer for the second one. So if you look at your what we call your R is given by negative value. Okay, so we know then in this case your relationship between number of room and kilowatt hours is in negative direction. So when we have negative direction, okay, so means that if x increases, y decreases. As as x increases, as the number of room increases, it seems that the number of the kilowatt hour will be decreasing. Okay, so I guess it because the more electricity is being consumed, I mean the more a room is being used, the less consumption of the kilowatt hours in terms of kilowatt hours. It could be tell that way. Okay, so in this case, so this is the uh, uh, what can we tell from the scatter plot. If we go to the direction of your sample correlation coefficient. Okay, so if let's say you don't have the what we call this particular R, what can you tell from your scatter plot is just based on your best guess from the scatter plot that you have. Okay, so for the second questions, okay, compute and interpret the sample correlation coefficient. Okay, so you compute using your Excel and you get your sample correlation is very small with negative value. So in this case, okay, the direction will be negative. Okay, and then in terms of the strength, very weak. Okay, you can say just weak or very weak can also. So what can you tell from this particular uh, figure? Okay, so you can see that let me click on okay, the R value indicates that uh, there is weak, okay, weak negative, okay, negative linear relationship between number of rooms and kilowatt hours. Okay, so that's how you can comment on the sample correlation R. Okay, class. Now, test whether there is a correlation between both variables. Use alpha 0.05. Let's go back to our uh, slide just now. Okay, so we have our scatter plot. Okay, but if you can see the direction, okay, if you base on this particular figure, it seems like you will have positive. But if you base on all the data from this particular value, so it will be somewhat not really, it will be very, a bit flat, okay, a bit flat. Now, let us test. Okay, first we have our hypothesis statement. No relationship between the two. Okay, no linear relationship between the two, or no linear correlation between the number of room and kilowatt hours. And there is a linear correlation between y, that is between the kilowatt hour and a number of room. Okay, and given alpha is 0.05 and our n is equal to 10. Okay, so our critical value will be 0.025 and the degree of freedom is 8. Okay, let us look at P distribution. 8, 0.025, you will get 2.3060. Okay, that's why you get, since we are dealing with two-tail test, again, plus minus 2.3060. Step 3, calculate for your test statistic using our given formula. So in here, you will get 0.037. A bit change, a bit different from the answer. Okay, if I'm not mistaken, okay, in the answer is given by negative 0.0356. I think due to their decimal point. Okay, but I think can be acceptable. Okay, once you get your T critical value and your T test, then we need to compare. Okay, so we have our T critical value is negative 2.3060 and our 2.3060 and our T test is negative 0.037, near to 0. So T test negative. So false in the rejection region means that we fail to reject the null hypothesis. Okay, so when we fail to reject the null hypothesis, so we need to accept that there will be no linear correlation. So there is insufficient evidence to conclude that there is a significant linear relationship between number of rooms and kilowatt hour. Okay, so that's how you conclude your uh, hypothesis testing for the if we base on the main topic just now is the population correlation coefficient. Okay, so based on our sample data, we don't have sufficient evidence to say that there is a positive linear relation. There is a linear relationship between number of rooms and kilowatt hour. Okay, any questions so far, class?
Is it the same if we say it has weak linear relationship and no linear relationship?
Can also. If you go back to your textbook, okay, uh, linear correlation, put as linear correlation. Okay, I think I missed out the linear correlation. Linear correlation, sorry class, is actually the same actually, but since we are referring to our R, okay, linear correlation. Correlation means hubungan, hubungan, relationship is actually hubungan also. So, but to be precise is correlation, okay. So significant linear correlation between number of room and kilowatt hour. What would be my correlation? Okay, thank you for your comment just now. Any more questions? Because the question asks about linear correlation. So go to what is being asked in your question. So if you're talking about linear correlation, then it should be linear correlation. Okay, class. Clear, class?
Clear.
Okay, thank you. Now we go to the third part, that will be regression equation. Okay, I hope by now you can um, uh, collect piece by piece. When we begin with the concept in the last class, theoretically, what is the simple linear regression? How does the simple linear regression is being measured? Now we have seen how we can do our scatter plot using Excel, and then we can use our Excel to help us out finding the correlation coefficient R, and then we can also test for the hypothesis testing for the population correlation coefficient, whether to know whether the two variables that we are investigating will have linear correlation or not. Now, we haven't seen what, how, and what, how does our models look like. Okay, we are talking about linear relationship. So, what is being described by that linear relationship? Okay, so again, class, go back to your basic concept of your population. Okay, since we are going to use our sample to make inference for our population, so we take our sample data. Now, if you have your data from your population, then you can have your what we call regression equation um, for your simple linear regression. So your simple linear regression will look like y capital Y is equal to beta naught plus beta 1 x plus epsilon. So this is your actual data or actual model based on population. Model based on population. But now since you are dealing with sample, okay, so since we are making inference using our sample, then using our sample, we are estimating our model. So estimating model using sample, that's why we have y hat equal to beta naught hat plus beta 1 hat x 1 plus epsilon. But in your case, this part will be left out. So we only stop here. Okay, so we have that model for our regression model. Now, every discussion that I'm referring to is referring to this one class. So we are using our sample data. That's why, okay, in our case, we are using this to come up with our model. And this one is actually describing the blue line. Okay, this is the blue line equation. Okay, so the whole blue line here is represented by this one. Now, if you look at your textbook, class, okay, the way we identify this particular line is based on what we call least square method. But since we are using our Excel, Okay, so if I'm not mistaken, our Excel is using the least square method, if I'm not mistaken. So that's why the discussion of the manual way on how we find this particular using least square method is being disregarded. So at the moment, we are focusing on using Excel to come up with this particular equation. Now, there will be few concepts that you need to understand with regard to this particular what we call scatter plot and the prediction line here or the model here. I think I'll just explain this afterward because I wanted to show you how we can come up with this particular line by using our Excel, how we can plot this equation uh, to represent our equation line. And how does we get the equation line? If you look at your in your textbook class, okay, if I'm not mistaken, in your textbook on page, this one is explained in on page 174. Now the discussion for the line, okay, how to get the line, how to draw the line, just to give you the idea on how to do it manually. Okay, it's being explained in page 177. So you can refer to this particular information on how the least square method and how to draw the line using the smallest point to your largest point so that you can have the line. Okay, so I would like to go straight away to the next discussion on how you can find your estimated model. This is what we call estimated model. Okay, estimated model. Okay, now manually, if you wish to find it manually, just to give you the understanding of how the beta 1 and beta not hat is being obtained. Okay, so this is how they are being calculated based on the sum of square of xy, yy, and xx. Okay, and they are also taking the value of the average of y and the average of x. Okay, so just to be quick for the manual on how the calculation of your model is obtained. Now let's continue to the next example by using the same exact data from example 5.1. Okay, you need to find the regression equation and sketch the regression line on the scatter plot of ordered pair. Interpret the slope. Okay, now this is your answer. How do I get this? Let's move to Excel again. Okay, now I have my data, mathematics score and physics score. Okay, I have X and Y. Okay, so I think I'll just show you from the beginning how we can get this particular um, scatter plot. Okay, once you have got your scatter plot, okay, change the horizontal what we call the horizontal beginning line, the figure, and the vertical figure. So put it so that it will be nicely sketched on your scatter plot. So let's say once I have changed the vertical and horizontal beginning value, so I get this. So what can you do to get the line and the equation? Go to the plus sign here. Okay, you will get the trend line. Click the trend line. Okay, and then go to the cursor, to the arrow here. Click, and then go to more option. you will be given this particular option. Okay, now I have my trend line, but I need my equation to be appear on the scatter plot. So I can choose display equation on chart. Okay, so if you so for the at the moment, just show the display equation on chart, and then you can change the font if the font is too small. Okay, go to home, go to font size, and I choose 18. Okay, now this is your equation and this is your trend line. See, the trend line should begin from the smallest, okay, point to the largest point, not beyond or not before or not beyond. Okay, so at the moment, class, for this, do you have anything to ask, class, before I go further to the explanation of the regression line? Do you have any question regarding the Excel?
No.
Okay, no, huh? Okay, thank you. Then go back to my notes because I need to explain, and this is the most important part that you are going to have to understand, because in your project later on, you are going to interpret this model. Now, imagine, class, from the beginning of our discussion, we begin with the scatter plot, we get our R, we get our hypothesis testing for our rho, whether there is a correlation, linear correlation between our X and Y. Now, we want our model to be appeared on our scatter plot, as well as the prediction line, the line, okay? So in this case, class, okay, so in this case, this has been done by Excel, and what next you need to know is how to interpret. Okay, class, again, remember your what we call your line, equation line, should not below this one, cannot, so it should start from here. So if you have line at this point, it will be wrong. Okay, you begin here and you stop at the maximum value. Stop here. Not beyond. If you get beyond, this is wrong. Okay, so that will be the first reminder. Next, I know my line begin from the minimum to maximum, and I know that my equation is y equal to 0.9944x minus 2.5294. And I would prefer to write this way, because I like the intercept is at the beginning. So y is equal to negative 2.5294 plus 0.9944x. Okay, so this is what we call the intercept. This is what we call the what? Delta 1 is the slope. Okay, is the slope. Now, class, remember, the slope belongs to whatever the coefficient of your x. Okay, you have your x here, so the coefficient here, we call it as the coefficient per kali. Okay, the coefficient is representing the slope. The slope is either positive or negative. If positive, that's how you have this particular linear relationship positively. Here also positive, right? So if it is negative, you will get negative here, and the equation will be somewhat like this. So please remember, class, if it is negative, so the slope negative shows that you have negative linear relationship, and here we'll get negative. at your R. So in this case, we have positive. So let's say okay, so we have positive. Oh my goodness. Okay, so we have positive. So this is our case. Now, the slope tells you whether you have negative or positive also relationship between your x and y. Now, what does this value tells you, class? Okay, how do you interpret this? Okay, now negative 2.5294 is the intercept of your y. Okay, if you go further, okay, this is your intercept at y. Okay, at y axis. Okay, your slope, okay, is the way how much is the stiffness of your slope equation just now. Okay, so how do we interpret? Okay, so this is the most important one. So if you can turn to your page on page 177, okay, 177, okay. So the way we interpret is this way, okay. Now, this is also this is your beta naught hat, and this is your beta 1. Okay. Now, what else should you know is that okay, 1 unit change in x, okay, 1 unit change in x. How would I say it? Should we put the question just now? Okay, interpret the slope. So the slope is this one. Okay, the slope is this one. Okay, so we are interpreting the slope. Okay, how would I say the sentence? Okay, okay. For 1 unit increase in x is mathematics score. Okay, for 1 unit increase in mathematics score, okay, on average, the physics score, okay, is increased by 0.9944 units. Okay, so this is the one that you need to understand. So if it is negative, so let's say if this is negative, okay, so how shall I conclude? Okay, so if it is negative, for 1 unit decrease in maths score, okay, on average, the physics score is decreased by 0.9944 units. So that's how you interpret if your slope either positive or negative. Okay, so be careful of what you have got in your model, whether it is positive slope or negative slope. Negative slope shows that you will have negative linear relationship. Positive slope shows that you will have positive relationship. Okay, so please make sure when you plot, make sure you know which one is your beta 1 hat which one is your beta not hat. And you should know what does it tell by beta not hat and beta 1 hat. Okay class, do you have any questions so far?
No.
No, okay. So if you don't have any questions, okay, so let us look at the example 5.8. So example 5.8 on page 178. Okay, find the regression equation for data in example 5.2. So we are talking about age and net worth just now. Okay, so we know that from our scatter plot, we hardly tell whether it will have positive or negative. But since we have our R correlation uh, correlation coefficient of our sample is given by negative 0.02 something. So we know that it will have negative correlation. So now let's look how does the plot of this particular equations looks like. Let's move to our Excel. Okay, so we have our age and net worth. Okay, if I plot, what do I have in my scatter plot is that, okay, my regression line is kind of flat, almost flat as our x-axis. And our equation looks like this. Okay, so we have y equal to 0.0097x plus 3.5527. Okay, so let's move to our, I hope I have copied the, okay, so if you look at the scatter plot along with the regression line, so you know that your equation is given by, so in this case, your beta 1 hat is 0.0097 and beta naught hat is given by 3.5527. Okay, so in this case, okay, since the equation and the regression line is almost flat, we cannot really use this model to interpret in terms of how does y change based on the change in age. Okay, so in this case, we are going to stop here because the model is too weak. The correlation coefficient is too weak, and then we know that the line is also almost flat, so we are not going to use this to make any interpretation because the model is not sufficient. Okay, so now class, can you someone tell me what is the time now? Class
10:25.
10:25, huh? Okay, class. Now, there are before we stop, there are few terms. I believe that terms can be found in your textbook, and then I believe that terms also bring some meanings to your understanding. Okay, so I hope whenever you see these particular terms, you know what does these terms refers to. Okay, when we say best fit line, what do we mean by best fit line? Class, based on this particular plot, if I were to rewrite again the plot, okay, I have my math here, I have my physics here, I have my plot, for example, here, here, here. Okay, when we say best fit line, okay, it will be the best line that fit your data. You may have different kinds of line. You can start your line by, okay, instead of having this particular line, I can have my line as this one. Also can. I can have my line this one. Also can. I can have my line, for example, this one also can. But which one is the best? Okay, that's why when we do use our least square method, least. Okay, the way we find our line, okay, the way we find our line is this one, okay, and this is based on the least square method, and based on the calculation of least square method. So that would be one way, the most commonly used to find the line. Okay, so best fit line means that is the best line that fit to your scatter plot. What is observed value? Okay, observed value is the value that is given in your data. So if I were to refer to this, so this is your observed value. All these are your observed values of x and y. Okay, so that is your observed value. So if you refer to your what we call scatter plot here, what is your observed value? These are all your observed value. Okay, all the dots here refers to your observed value. Now, what is error? When we are talking about error, class, when we are talking about error, okay, we are talking about because the aim is to have the best fit line. And in this case, using this square method, this is my best fit line. But when we draw our best fit line, there will be cases where the observed value will not touch the best fit line. For example, we have this observed value to the line. So the distance between the observed value to the line is what we call error. Here, small, here is the error. Okay, very small here is the error. Here is the error. Okay, here is the error. Okay, is the difference between the observed to the predicted line. We also use this as the prediction line, but later we'll see what is being named by predicted line. Least square regression line. Least square regression line is also the same as best fit line, referring to your line here. Okay. Now, predicted value. Class, this is very important. What is predicted value? Okay, predicted value is all the values on the line. For example, if this is my observed value, okay, this is my observed value. This is my predicted value. Okay, this is on the line here is my predicted value. Okay, here also predicted value, here also predicted value, here also. Any points on the line is what we call predicted value of y using our x. What x? Here x is 65. Here our x is, let's say, 73. Here our x is let's say 75. What is my predicted value? That will be my y. What is my y here? Is 63. What is my y here? Is 68. What is my y here? Is 72. So at every single x on the predicted line, you can get your predicted value of your y. Class, can you understand that so far?
Yes.
Okay, thank you. Now, population linear regression. Okay, so this one is referring to your y, capital letter Y, equal to beta naught plus beta 1 x plus epsilon. Sample linear regression, that would be y hat beta naught hat plus beta 1 hat x. Okay, regression equation, this is your regression equation. Okay, this one is your regression equation. Regression line is referring to the line, this one. Regression line is the same as best fit line, least square line. Okay, so almost sharing the same meaning. Now, slope intercept, we know that this is our slope. This is our intercept. Okay, intercept. This is our slope. Okay, so at the moment, I want you to understand the whole concept and terms about simple linear regression. And if you can look through, there will be some properties, okay, properties regarding the least square regression line. Also properties of residual. Since residual will be among the things that you need to include in your project too, I think I will cover that somewhere next week. Hopefully by next week I can finish the rest of the chapter 5. Okay, so properties of residual. Okay, so what is the time now, class?
10:34.
Okay, 10:34. Now I think I'll just stop here. Okay, I'll finish I think the rest of the chapter that will be on page 177. Okay, until residual analysis. Okay, so page 178. So for page 178 until 186, okay, I will cover this next week. Okay, now class, okay, do you have any questions for the things that we covered this week, class? Any
No
questions?
question.
No question. I feel like you are the only one student in my class. I can only hear your voice. I cannot hear the rest of your friends' voice. So thank you very much for giving me such a good response. Okay, so I'll just stop sharing. Okay.
We are also here, Doctor.
I